This is Science Unwrapped. And I am Brynja Kohler. I'm the Associate Dean of Undergraduate Programs and Services in the College of Science. And tonight I'm here as chair of the Science Unwrapped Committee. And we're very happy to have you here with us for the last of our series of, at least for this spring semester, where we are celebrating undergraduate research. So I have any of you been here to a Science Unwrapped before? Show me your hands, raise them high. All right. Who has never been here before? Did we got anyone in the audience? Welcome newcomers, that's awesome. Okay, so for those of you who are new, we always start with a talk, and it'll be about half an hour, a short talk, and then we have a little break. And if at that time you'd like to excuse yourself, you can, or you can stay for questions and answers. So we'll have a little intermission break, and then you can stay for questions and answers, and then everyone can explore the tremendous activities that we have out in the hallways. We have lots of volunteers, different clubs and community organizations have brought some hands-on learning activities out there, and we have refreshments. We also feature tonight some undergraduate research posters, and their topics are a wide range of things, from an enzyme important for our cardiovascular health, to the use of computer vision tools to catalog river rapids, and we have a poster on the STEM gender gap, and on new discoveries about Utah's ancient geology. So be sure to stop by and visit these undergraduate research posters, again, for our celebration of undergraduate research. So this year, I want to, because this is our last, and you can see the flowers blooming out on the quad as you walk by the geology building. It smells fabulous, and the mountains are white, and the grass is green. I know you're getting ready for summer. So I just want to really extend a heartfelt thank you to all the volunteers that have worked so hard this whole year, making these activities possible, and to all of our speakers. We greatly appreciate the time and effort you put into creating wonderful activities, and we look forward to welcoming our audience back, as well as our volunteers, in the fall, where we will continue our celebration of undergraduate research. All right. Next, I just want to give another thank you to some VIP guests. Our Dean, Michelle Baker, is here tonight, as many nights, with Science Unwrapped. And then now I have the pleasure of introducing our speakers. We have USU mathematicians Matt Young and Seth Porter. Dr. Young is an assistant professor in the Department of Mathematics and Statistics. He is from Canada and earned his undergraduate degree from Queen's University in Kingston, Ontario. He earned a doctoral degree in mathematics from New York's Stony Brook University and completed postdoctoral fellowships at Germany's Max Planck Institute for Mathematics and the University of Hong Kong. His research interests lay at the intersection of representation theory, geometry, and algebra, along with related mathematical physics. Dr. Young is joined this evening by undergraduate scholar Seth Porter, who comes from Lehigh, Utah, and graduated from the Carl G. Macer Preparatory Academy. Seth is the College of Science Scholar of the Year, a top honor at Utah State. He was named a 2024 Peak Summer Undergraduate Research Fellow and also received a USU Undergraduate Research and Creative Opportunities Grant to support his research. Tonight, Seth and his mentor, Dr. Young, will discuss their mathematical research on knot theory. Let's welcome Dr. Matt Young and Seth Porter.
Great. So thank you, Dr. Kohler, and thank you, everyone, for coming tonight. So as Dr. Kohler said, my name is Matt Young. I'm assistant professor in the math department. I've been at USU for about 5 years. And so two of my main areas of research are algebra. So people here probably have some idea of what algebra is. There's also another branch called topology, and I'll try to explain throughout the talk why my studies in those two areas kind of naturally led me to think about knots.
Perfect. And as Dr. Kohler was saying, my name is Seth Porter. Last summer, I was a Peak Summer Research Fellowship, and I also received an ERCO grant. And I used those to sort of work on the research here that I'll be presenting today with Matt Young. And this is a great opportunity to showcase how wonderful USU is at funding undergraduate research. And I hope that many of you will be able to receive the same opportunities. Okay, great. So we have this thing on the slide behind us called untangling knot theory. But many of you may be wondering, what exactly is a knot? So perhaps there's a few people in the audience who can put forth suggestions for what they think a knot is. Yes, in the back with the orange shirt. Of course, that's a great example, a tangle of string. That's a wonderful example of a knot. Any other suggestions? I know you guys have seen knots before. Anyone else? There's no points given for wrong answers. Yes, right there.
Sort of a long string or rope or something of that sort of nature that is configured into something that is hard to undo.
Exactly, that's totally right. Okay, wonderful. So these are great examples of knots, and I think another good example of a knot that we all see every day is our shoelaces. We use shoelaces every day. We need them. We tie them to keep the shoes on our feet, and it's wonderful. So that's an example of a knot that I would think is pretty useful and pretty handy. We also have Christmas lights. Those are a very bad knot, I feel like. You get your Christmas lights out every December. It's always super tangled up. It's a giant ball. It's a mess, and it's horrible, and it takes forever to get undone. Okay, wonderful. These are all great examples of knots that we probably see fairly frequently, but they are not technically mathematical knots. And the reason we make this distinction is that in mathematics, it's incredibly important to use precise definitions. The reason we need these precise definitions is that precise definitions will allow us to prove theorems, and we'll see a couple examples of those theorems later on. So, why do the ends of a knot have to be tied together? Well, the reason is if the ends of the knot are not tied together, you can always untangle the knot. So imagine this extension cord down here. This is something that also tends to get knotted up. And we can see we have a knot in the middle right here. But since the ends are not basically plugged into each other, we can fairly simply untangle the knot, like so. And now we have this sort of free extension cord. And you can imagine that if this thing was even more jumbled up and tangled, it may take a while, but you could always untangle the extension cord. However, if the ends are plugged together like so, notice we have this sort of knot in the middle, but now it's stuck here. And there's no way to get rid of this knot without unplugging the extension cord. Now, some of you may be thinking, maybe I could sort of fiddle around with it for a few minutes and, I don't know, maybe try something like this or maybe something like this. But notice the knot is still here. And in fact, if you don't unplug the extension cord, it will take you, well, forever to untangle this knot. It will be stuck here forever. So, that is a mathematical knot. Now, knots in mathematics can be very simple or very complicated. So on the screen behind me, we have some examples of very common knots. We have the unknot in the top corner right there. It's just this circle. It's basically the simplest knot in mathematics, not very interesting or complicated. We also have the trefoil knot right there. Some knots are used so commonly that we just give them names. So that's an example right there, the trefoil knot. It has 3 crossings, and we'll see it again later, a little bit later. We also have this cinquefoil knot right there. It's sort of on the bottom row, and you can see it sort of looks like this star, and that's another knot we'll see later on. So these are some examples of relatively simple knots that people have classified. We also have a very complicated and very famous knot. This is called Thistlethwaite's knot, and it's just an example of how complicated these knots can be. And once again, we'll be looking at this guy later on in the talk.
Great. So now that we know what we're going to be meaning by a knot in this talk, I want to talk about an important question, which is, when should we think 2 knots are the same? Okay, and the definition, this is really why knot theory is related to topology. Okay, the definition is, we want to think 2 knots are the same if I can move around one knot by kind of stretching it, pulling the strands, maybe looping it and so on, to bring it to the other knot. Okay, but I'm not allowed to do operations like cutting the knot or gluing one part of the knot to another part of the knot. So for example, the knot on the left, this is the trefoil that we saw before, okay, the blue one. And the red one, you can see it looks slightly different from the trefoil. In the middle, it looks like I've kind of maybe crushed the pieces together a little bit and so on. Okay, but I haven't done any operations like cutting the knot or gluing parts of the knot to another part. Okay, so we want to think of these two knots as the same. Okay, and so for example, what would it mean then for a knot to be the same as the unknot? That's just another way of saying you can untangle that knot. Okay, so that's what it means for two knots to be the same. Now, as a warm-up to make sure we understand this, I've drawn on here 4 pictures of knots. You should think I'm drawing them on a screen, so I have to write which part goes over, which part goes under. So if we see diagram A, that's the unknot, just a loop. Okay, can I get a show of hands? Does the knot A and the knot B, are they the same knot? Amazing. Yes, they're the same knot, because all I've done to get from A to B is I add a kind of twist at the top half of A. Okay, similarly, to go from B to C, I just add a second twist. Okay, so the knot kind of looks more complicated, but it's just an artifact. It still is just the unknot. What about A versus D? Can I get a show of hands if they're the same? Again, yep, you just pull one strand across. Okay, and so those are the same. Okay. Now, what about the unknot and the trefoil? Can I get a show of hands who thinks those are the same knot? Get some thumbs down. Okay. And I agree. When I first look at this, they're probably not the same. And Seth was unable to untangle it in a couple minutes. But who's to say that Seth, after working for an hour or 2 hours, wouldn't untangle it? Okay, so we're probably quite confident they're different, but we're not certain in the mathematical sense. What about the trefoil and the cinquefoil? Who thinks these are the same knot? Okay, so now there's some hands that they might be the same. And to me, it's getting kind of complicated enough that I'm no longer as certain, at least as the trefoil versus the unknot. Now we see Thistlethwaite's knot, which all you should think is it's a jumbled mess of string. Who thinks this is the same as the unknot? Okay, now it turns out that Thistlethwaite introduced this knot exactly because it is the same as the unknot. So it shows you that even a very simple thing like the unknot, it can masquerade in something that looks extremely complicated. Okay, and so we need some tools to be able to, 1, decide whether 2 knots are the same, and 2, to actually be able to kind of use these tools in rather complicated knots.
Okay, so Matt has just spent a few minutes telling us about sort of how we can tell whether or not 2 knots are the same. And this seems like an interesting problem in and of itself, but in general, why should we care about sort of these knots and whether one thing is the same as another? Well, in science, we often want to classify objects. That allows us to understand them more. And on the screen behind me, you'll see an example of perhaps the most famous and impactful classification in science, the periodic table of elements. Now, this is a classification of all of the elements that make up everything in the universe. So me, you, pizza, desserts, everything in the universe is made of these elements. And throughout history, people have discovered ways to classify these elements. And it's been very helpful and useful. Well, similar to how people have classified elements, many mathematicians and scientists also want to classify knots. So where here we have the periodic table, here we have the periodic table of knots, which is basically a classification of knots. And we can see sort of knots organized by defining characteristics. So on the periodic table, elements are organized by their atomic number. And the atomic number is the number of protons in the nucleus of each atom. And that is the distinguishing characteristic of each element. Well, much as atoms have distinguishing characteristics, knots also have distinguishing characteristics. So if you look sort of the purple square on the screen behind me, you'll see our friend, the unknot. And it has 2 numbers above it, 0 and 1. Now, it has a 0 because it has no crossings. If you look at the unknot, there's no sort of tangledness in it. And it also has a 1 because it's the first and only knot with 0 crossings. We can also see the trefoil sort of in the lime green on the top row. And it has a 3 because it has 3 crossings, and it has a 1 because it's the first knot with 3 crossings. Naturally, we can sort of repeat this process and continue to classify knots. So we can see a knot with 4 crossings, and we can also see the cinquefoil sort of on the far right of the screen, and it has a 5 and a 1 because, once again, it's the first knot with 5 crossings. Only in this case, we have another knot with 5 crossings, and we give this 5-2. Now you can imagine that you could do this and classify all these knots, and this would be very useful. As it turns out, in the 1800s, at the same time as the people were discovering elements, they were also discovering these knots. And they thought that elements were actually knots. That is, if you were to take an element, say iron or gold or something like that, then that thing actually was sort of a knot floating around in space around us. Well, as it turns out, this theory didn't really work out. Initially, people thought something like the unknot was hydrogen, and something like the trefoil was carbon. But if you know a little bit of chemistry, you'll know that the second element isn't actually carbon, it's helium. So as people sort of discovered more of these elements, they realized there's no good way to link all of these elements and these knots together. So the theory was eventually discredited. But I think that's okay, because that's something that happens a lot in science. People propose theories and ideas, and sometimes they turn out to be correct, and sometimes they turn out to be wrong. But in the process, we learned a ton about knot theory.
Okay, so now that we've kind of isolated this question of we need to decide when 2 knots are the same, I want to talk about some of the tools that mathematicians have developed in about the last 150 years to try to understand this question. Okay, and so the basic idea is kind of summarized in this diagram. Okay, so we have the blue knot in the middle. This is, again, our friend the trefoil. Okay, and it's a knot. It's a 3-dimension, it's some kind of string wound in 3 dimensions. It's rather complicated. Okay, and the basic idea is instead of looking at the 3-dimensional object directly, we want to kind of look at its shadows from various perspectives. Okay, so I've drawn here, so we see the knot, and there's kind of 3 walls, 2 behind it, 1 below it, and you can see on those walls we've drawn the shadows. Okay, now I've redrawn them in red, green, and blue. Okay, and in those red, green, and blue diagrams, there's actually a little bit more information than the shadow, because I've drawn, well, where does one strand cross over another strand versus cross under it? Okay, the shadow doesn't have that information, but these diagrams do. Okay, so I'm going to call these knot diagrams. Okay, and so the idea again is we take the complicated 3-dimensional thing that we're interested in understanding, and we replace it with a simpler 2-dimensional thing that we can try to understand. Now, I need the previous. So we already see a problem, though. Okay, if we're interested in the 3-dimensional knot, we see that each of these 3 diagrams, they're actually different. Right? The blue diagram on the right, this is the standard picture of the trefoil we've been looking at. It has 3 crossings where one strand crosses over another. On the other hand, when you look from a different perspective and you get the red diagram, this one now has 4 crossings. Okay? Similarly, the green diagram is different. So the same knot, it can have many rather different looking diagrams. Okay? But luckily, there's a way to control this ambiguity in the diagrams. Okay, and this is the work of a mathematician named Kurt Reidemeister in about the 1920s. Okay, now what Reidemeister discovered was that if I give you a knot and I look at all of its various knot diagrams, so kind of shadows from all the different perspectives, then these knot diagrams differ from each other just by a sequence of extremely simple moves. Okay, these are now called the Reidemeister moves, and they kind of form the backbone of modern knot theory. Okay, so I've drawn on the left the 3 Reidemeister moves, and Seth is going to illustrate them. So the way to understand these diagrams, first of all, is you should think you're zoomed in on some small part of the knot, okay, and the rest of the knot is kind of unchanged. So these pictures don't look like knots, but you should think beyond those pictures there's some kind of knotting happening. Okay, so we're just changing things in a small area. Okay, so the first Reidemeister move says you take a straight part in your knot, and then you just add a loop like that. Okay, that's an operation that doesn't involve cutting or gluing, so it doesn't change the knot, but it does change the knot diagram. Okay, we see in diagram 1, there is introduced a crossing. Similarly, in diagram 2, which we have here, so we have 2 parallel strands, and all we do is pull one strand across the other. Okay, it definitely does not change the knot. The diagram will look different though. Okay, and third, this is called Reidemeister 3. This is the most complicated one. It says that if you have a crossing, like so, if you have a crossing and you pull a string all the way in front of it from side to side, that doesn't change your knot. It does change the diagram. Okay, and so again, what Reidemeister showed is that by repeatedly doing some possibly very complicated sequence of these 3 moves, you'll always be able to get to one diagram from a knot to any other diagram. Okay, so the complication lies in the fact that, for example, if you try to do this for the Thistlethwaite's knot, you're going to be there for a long time, but you can do it. Okay, so if we return to our example of the 4 different pictures of the unknot, we see that diagrams A and B, they're related exactly by a Reidemeister 1. I just introduce a twist. B to C, I introduce a second twist. And A to D is Reidemeister 2. I pull a parallel strand across. I didn't draw Reidemeister 3 because it's a little bit more complicated in this example. Okay, so it's great if we can kind of organize these diagrams and relate them via Reidemeister moves, but if it's so complicated in kind of interesting examples to do this, well, what should we actually make of these kind of diagrammatic calculus? Well, this is now, it turns out that this gives an example in mathematics of what's called a knot invariant. Okay, knot invariant is just a fancy word for a property of a knot. Okay, so it's just some fundamental property that a knot has. And again, this is kind of where I came into this story because in topology, the main thing you do in topology is kind of assign invariance to spaces with kind of similar properties. So this is something that I was trained in, and so is where I got into the subject from. Now, everyone has with them a piece of paper and some crayons. Okay, and so what we want to do is understand kind of the most basic example of what a knot invariant is. Okay, and so this is called tricolorability. Okay, and it asks whether a knot diagram can be tricolored or not. Okay, now here's the rules of the game. Okay, everyone should have 3 colors. I've drawn red, green, and blue on the board. Okay, and so the rules of tricolorability are as follows. Okay, so each strand of your knot diagram, you have to color with exactly 1 color. Okay, so the only time you can change colors is when you have to pick your pen up as you make a crossing. Secondly, in your diagram, you need to use all 3 colors. Okay, and third, anytime you see a crossing, you need to see either 1 color or exactly 3 colors. Okay, so let me do a quick example. So I've drawn the unknot here. Okay, so the unknot, so I've got blue, I guess. So notice the unknot, it has a single strand. So by the first rule, I have to color that with 1 color. So I do that. Okay, but now I can't satisfy the second rule because I need to use all 3 colors. Okay, so this diagram, I cannot tricolor. Okay, well, that one was pretty simple. What if I look at this version of the unknot, but where I've added 3 twists? Okay, this looks better because now you see it has 3 strands. Okay, so I color those 3. I can meet the rule of using all 3 colors. What's the other one? Green. Like this. Okay, but now I'm in trouble because I don't satisfy the third rule. For example, if I look at this crossing here, you see I have 3 incoming, or rather I have blue and red at that crossing. Okay, I was only allowed to have either one color or three colors. So again, this is not an admissible tricoloring, so the answer is no, it cannot be tricolored. Okay, and so, oops, I gotta go back to this thing. So, current slide. Okay, and so this picture here is just, we've seen all these different ways of thinking of the unknot, and the answer is the same for all of these diagrams. No, you cannot tricolor it. Okay, and now this is not a special case, this is actually a totally general fact, and you can see it by studying a colored version of these Reidemeister moves. Okay, but the point is, tricolorability, it's going to, every diagram of a knot is going to have the same tricolorability property. Okay, so it's really a fundamental property of the knot, not of its diagrams. Okay, and in the end, we're interested in the knot. Okay, and the punchline for us is that if we have two different knots, one of them is tricolorable, one of them is not tricolorable, we can 100% confidently say those knots are different. Okay, that's the punchline for us. So let's take a look now. So on your sheet, I've given you three knots. So these are the trefoil, the cinquefoil, and a more complicated knot, which is just called 7-4. Okay, so I'm going to give everyone a minute to try to tricolor the trefoil. Okay. Did anybody have success tricoloring the trefoil? Awesome. Yes. So I've drawn here an example of a tricoloring. Okay, so I've used all three colors. Each strand is colored with one color, and at each of the three crossings, all three colors are there. So we already now have our first result. We know that the unknot is not tricolorable. The trefoil is. So now we know with 100% certainty the unknot and the trefoil are different. You cannot untangle the trefoil. Did anybody make any progress on the cinquefoil? That's also good, actually. If someone said they managed to do it, that was going to be a bad sign. So it turns out that the cinquefoil cannot be tricolored. Okay, and I've drawn an example here where I kind of start trying to do it. Okay, so maybe if I start at the bottom right in blue, I just move counterclockwise. I choose colors each time to meet all the rules I can. But by the time I get to the fifth leg, the black part, no matter what color I color it, I'm going to break the rule that at a crossing, I need one or three colors. So this is not a tricoloring because I can't choose the color of the final black leg consistently. Okay, that's also good because now the trefoil is tricolorable, the cinquefoil is not. Again, we know with 100% certainty the cinquefoil and trefoil are different. You can't kind of tangle the trefoil to get to the cinquefoil. But one thing to point out is that, unfortunately, the unknot and the cinquefoil, we don't learn anything about them relative to each other. Because neither of them are tricolorable, it just doesn't tell us anything. Okay, now there's one more knot here, the 7-4. I'm going to leave that if you want to play around with it through the rest of the talk. So now we have our first knot invariant, and so we've already answered a couple of the questions from the start of the talk.
Okay, great. So Matt has just spent a few minutes telling us about this wonderful knot invariant tricolorability. But as we can see, there's a problem. We still aren't sure if the unknot is different from the cinquefoil. And most of you earlier on in the talk voted that you thought the unknot was different from the cinquefoil. But who's to say we can't just do a few more Reidemeister moves to get the cinquefoil back to the unknot? Turns out we need more powerful forms of knot invariance. And this is where a lot of mathematical research in the last 30 years comes into play. In particular, something known as the Jones polynomial. And the Jones polynomial was developed by a man named Vaughan Jones, and you can see a picture of him on the screen behind me. And for this, he was actually awarded the Fields Medal in 1990, which is often called the Nobel Prize of Mathematics. Now, it's key to remember that the Jones polynomial works very similar to tricolorability. That is, there are certain rules and properties of the knot that we use to assign a polynomial to each knot. And the key thing being, if two knots have two different Jones polynomials, then those knots are different. First, what's a polynomial? Well, it's just really a collection of symbols. Think of it as a more complicated number. So, on the screen behind me, we can see our old friend, the unknot, and it gets, by convention, a Jones polynomial of 1. Nice and simple. We can also see the trefoil, and it has this Jones polynomial, this negative q to the negative 4. And we can see, once again, it's different from the unknot. So, we know the trefoil's not the unknot. But tricolorability already told us that. However, now we look at the Jones polynomial for the cinquefoil, right there. And we can see that the Jones polynomial is different for the cinquefoil, the trefoil, and the unknot. So now, at long last, we know the cinquefoil is not the same as the unknot. As an added bonus, we know the cinquefoil is not the same as 7-4, because 7-4 has a different Jones polynomial. So, looking at this, we can see the Jones polynomial has allowed us to distinguish 4 knots. And this is wonderful. It's not that wonderful, though, because as it turns out, if you look at more complicated knots, they can have the same Jones polynomial. So we have on the screen behind me 2 very famous knots called the Conway knot and the Kinoshita-Terasaka knot, and these are 2 knots that are actually different but have the same Jones polynomial. And if you look sort of at the bottom edge of the screen, you can see where these knots differ. They're very closely related, but they are different. But they have the same Jones polynomial. So clearly, more research is needed. Now, this is where a lot of modern, ongoing mathematics research comes into play. In particular, a knot invariant known as the Z-hat invariant. And this is actually the work that Matt and I worked on last summer. We used work by a PhD student, Adam Robertson, who is in the crowd today. So if you want to learn more about knot theory, find him after the talk. And we used this Z-hat invariant to help build another knot invariant. And once again, the way it works is relatively simple. We use a branch of mathematics called quantum algebra, which is the mathematics underlying quantum mechanics and quantum physics, and from that, we use rules of quantum algebra to assign invariants to each knot. And once again, if a knot gets a different invariant from another one, we know those 2 knots are different. So that's how the Z-hat invariant works, and it uses this nasty-looking, horrifying formula behind us. Now, we've spent a long time talking about knot invariance and distinguishing knots from another. But why should we actually care about all of this? Well, as it turns out, scientific research and mathematical research are very especially linked. Many of the wonderful achievements of modern science that allow us to live such wonderful lives would not be possible without the equally wonderful achievements of modern mathematics. Now, we're going to tell you about one quick example. DNA is the stuff of life. It encodes the information that we need to live. So, DNA has all the information that you need as a human to function. DNA is so important, in fact, that each cell in your body has 6 feet of DNA. 6 feet is almost as tall as Matt and I are. Now, there's a lot of cells in each body, so there's actually enough DNA in the average human body to make a line of DNA going from the Earth to Pluto and back 5 times. So that's a lot of DNA. Naturally, because DNA, there's so much of it in each cell, and cells are very tiny, what can happen to this DNA? Well, it can become tangled. it can become very tangled and, in fact, knotted. So this is where we see the wonderful union of mathematics research and science. It turns out that if DNA is knotted within a cell, say it's in the form of something like a trefoil, then the cell cannot reproduce. Essentially, the cell cannot function, which turns out to be a problem, as you can imagine. Now, there's a special enzyme in each cell called a topoisomerase that works to, in some sense, unknot the DNA. Now, the way this works is the topoisomerase actually makes cuts to the knot to turn, say, something like a knotted DNA in the shape of a trefoil back to the unknot. How does this work? Well, the topoisomerase goes through and it makes strategic cuts, and we go from something, say, the trefoil back to the unknot. And on the screen behind me, we can actually see an electron microscope image of DNA in the form of the trefoil. And once again, the topoisomerase will turn that back into the unknot, and then the cell can effectively reproduce. And this is all a very wonderful process. Well, it turns out that knot theory gets even more important here. One of the big problems with cancer is that it's cells reproducing uncontrollably. Well, how do you stop the cells reproducing? You can keep the DNA tangled together. And then the topoisomerase, if you can inhibit that, it can't untangle the DNA, and the cells can't effectively reproduce. So we use knot theory and modern biological research to inhibit the topoisomerase, and that allows us to develop more effective chemotherapy drugs. And once again, this is just one example of the wonderful union of mathematics and modern scientific research. So, the next time you're sitting in class, in math class, and thinking about how useless all of this is, I want you to remember how important mathematics research is for all of the wonderful things we have today. And the next time you see, say, a jumbled pile of string or a shoelace, maybe you can think about whether or not that thing is the same as the unknot. Thank you.
All right, let's get started. There's a question right up here in the front.
Do you have computer software to determine the Jones polynomial from a knot diagram?
Yes, so the question is there computer software to compute the Jones polynomial from a knot diagram? So definitely. So Seth spoke a little bit about how we use something called quantum algebra, whatever that is, to define the Jones polynomial. So quantum algebra, in like less fancy terms, it tells you various matrices, so like some numerical information that satisfy lots of consistency conditions. Okay, and so the way that we program that into a computer is each time you see a crossing, you attach a matrix to it. Each time maybe you see a part of like this of a diagram where it's closing, you take what's called the trace of a matrix, you just add up the diagonal entries. And so it's very computable using what's called linear algebra. So you can compute very complicated knots, the Jones polynomial, relatively quickly. So that's, and to be clear, I did not compute those Jones polynomials. I used a computer to compute them because, yeah, for exactly that reason, yeah.
Great talk, thanks. Could you give us some beginner's insight to where the terms of the Jones polynomials come from by putting that slide back up there where you showed a few examples of knots and then the Jones polynomials under it? I mean, without getting too, so where the exponents come from and what determines if we see a plus or a minus sign in the term?
It's actually quite complicated to explain individual terms. And so the reason for that is, so let's take a look at the trefoil. It has three terms, whatever they are. Okay, in this calculation of the Jones polynomial, there's kind of many intermediate stages. And in those intermediate stages, there's usually a huge number of terms, and they cancel at the end. So for example, this, just to take the first one, minus q to the minus 4. This is probably coming from 5 or 6 terms who's maybe like 1 plus 2 minus 5, all with that coefficient. So it's very hard to isolate. You can't see where an individual term in the answer comes from without looking into the kind of guts of the calculation. And there it's extremely complicated because it's involving a rather large matrix, and the matrix entries have various powers of Q in them.
So is there any connection one can see to the polynomial to the number of crossings or the number of loops, or is that buried too deeply in the origins?
So you can see something about the minimal number of crossings. So as we've seen, for example, the unknot, it has value 1 for whatever reason. But we can also make a very complicated version of the unknot diagram by just twisting it. So and that's also going to have Jones polynomial 1. So you can have as many twists as you want, and it will not change the Jones polynomial. Okay, but what you can say is that if you look at maybe like the largest exponent which appears, you can relate that exponent to the minimal number of crossings for such a diagram. So we do have like qualitative statements like this. But in the end, so we use the word quantum algebra. So it is some kind of quantum thing. And we know from other experiences in physics, like sometimes quantum things, they don't have easy classical analogies. And this is really one example of this. The types of things that you're looking for in tricolorability, these are kind of classical things we can understand. The Jones polynomial is its own beast, and it's hard to kind of look directly into it.
Thanks for that presentation. I got a question about cancer research, and maybe it's outside the scope of what you guys do. So are cancer drugs just intentionally knotting or creating knots in the DNA? So you talked about chemotherapy. Is this the purpose of what chemotherapy is doing to try to slow down the reproduction of cells?
So in particular, there's like several kinds of chemotherapy drugs, not all of them. And the way they work is they sort of stop this topoisomerase, which is like this particular enzyme. So the cell kind of like recognizes the need to reproduce, but if the DNA is all knotted, essentially, then this topoisomerase sort of enacts itself and will sort of uncut the DNA, like I was saying, and that will allow the cell to reproduce. But if you can sort of stop this topoisomerase, then the cell won't be able to reproduce. So that's like my very, I suppose, surface level understanding of how it works.
A rock climbing rope? Is that a knot?
Yeah, so the question was, is climbing rope a knot? And I would say, yes, it's a very useful knot that we use, but it is not technically a mathematical knot unless the ends are sort of glued together, like I was saying at the start of the talk, because with a climbing rope, if you say tie the knot improperly, then the knot can come loose, and the consequences of that would be rather unfortunate, I think.
What exactly is a knot?
Okay. So a knot is, okay, so you're wearing, I can't see if you have shoelaces or not. So say you have a shoelace. Okay, so you take your shoelace, and however you jumble up that shoelace, as long as at the end you tie the two ends together, that is a mathematical knot. Okay, so the key point is really you need to tie the ends together, because if the ends are not tied together, we know that if you have enough patience, you'll be able to thread it through itself and undo it. So we're really interested in mathematics in knots that there's no way that you can possibly undo them.
Okay, I just want to clarify, I may be way off, but does the quantum algebra basically structurally codify in 3D the Reidemeister rules?
So if we go back, it's way too far back, and we look at the Reidemeister moves. So maybe I want to talk about this. So if we kind of just, I re-summarize what happened on this slide. On the left hand, we wrote some rules of how to do things with diagrams, okay? We happen to use English language to write those rules. Okay, the rules are pretty simple. And the Reidemeister moves, they allow you to check that actually these rules, which are talking about knot diagrams, are actually describing something about the knots. So these rules have some kind of consistency with the Reidemeister moves. Quantum algebra, it's whatever it is, it's some language that allows you to very naturally write these analogs of these rules. So we don't write them in English anymore, now we use quantum algebra, and it's so well behaved that it's also consistent with the Reidemeister moves.
Are there other extensions of quantum algebra?
Yep, yeah, there's quantum algebra is the one that I was trained in, and so for me, there's no other extension. But definitely for people who are kind of have more calculus background, there's some version of, you can do constructions like this using calculus type techniques.
Oh, I don't mean replacement. I mean, can you use quantum algebra for other modeling other systems, for any other?
Definitely.
Yeah.
So for example, so quantum algebra, it's the thing that describes elementary particle physics. You get similar applications of knot theory in quantum computing. So in quantum computing, you're interested in some kind of particles that knot around each other, and they basically provide the qubits, so the computing power. And so quantum algebra, this is actually the kind of scientific application I'm most familiar with, is the application to quantum computing. So it has kind of anywhere there's quantum algebra. And there may or may not be knot theory, but quite often there is. Yeah, thank you.
Do Mobius strips relate to knot theory at all?
Yes, yeah, definitely. So a Mobius strip, probably many people, there's no paper here, but take a strip of paper, instead of gluing it at a twist before you glue it, it's a Mobius strip. So if an ant walks around on one side, it will end up on the other side. It's a one-sided piece. And so you can think of a Mobius strip, it's kind of like a knot. Well, these knots, you should think they're kind of infinitely thin. Okay, but if you fatten the knot a little bit and you think of it as like a ribbon, then you can get a Mobius strip. You could do more complicated versions of Mobius strips. So definitely, and actually, if I'm being completely honest, we actually needed most of these things to be ribbons for the statements we're saying to be correct. So the Mobius strip is very related, but it's much harder to draw than the knots.
Are there other questions? Oh, I see someone.
First of all, please forgive me if this sounds dumb. I'm not a mathematician. But is it meaningful, or are there any applications to knot theory in dimensions other than 3?
Okay. So yes, the short answer is yes, but it's much harder. So it turns out that, okay, 3 dimensions is kind of the right dimension to do knot theory, because we managed to find some knots that are really knots. You can't untangle them. It turns out if you think about a knot but living in 4-dimensional space, all of them can be untangled. Basically, like there's an extra dimension, you can kind of pull the knot suitably and untangle it. So if you study knots in 4 dimensions, unfortunately, it's not very interesting. However, you can do something slightly different. You can, instead of looking at basically a 1-dimensional thing, a string wrapped around itself, you can imagine a 2-dimensional thing like a donut wrapped around itself. Now you can do that in 4 dimensions. That's an interesting theory. It's much more complicated, but this is higher dimensional knot theory. And it looks rather different. You use totally different techniques, but it's people are thinking about this.
Wonderful questions, everyone. We've got one more.
Thank you. I was just a simple question for the periodic table of knots. The secondary number, what was that? Just like the order in which it was described, like initially documented?
Yeah, so as I was saying, like in the 1800s, people were sort of just like looking at these knots because they thought they were interesting. The thing was they didn't have a lot of this theory we've talked about, so they didn't really know what like Reidemeister moves were. They didn't have tricolorability or anything like that. So what people would do is sort of just like create these knots and then sit there for a while and try to basically move them around until they got another knot. And so yeah, that's totally correct. Like the little numbers you see, basically it's like the order in which they were discovered. So it makes sense that you sort of see the cinquefoil first. There's actually a process you can use to sort of generate these like, I guess, star-looking knots. So you have like the cinquefoil, you have this 7-1, and so these are the knots that were discovered first. And then as we move along the table, you see like all these more complicated ones. These are ones that people sort of had to play around with to get to. And the funny thing about this is like people basically created a table of these knots up to, I forget the number of crossings, it's like 11 or 12, so up to some high degree of complexity. And it took like decades for people to realize that there were two knots in the table that were actually the same, but they thought they were different. So this is just like, I don't know, a little insight into how difficult this can be.
So everyone else can hear. Do people use the periodic table arrangement to generalize like what other knots may be?
Yeah, it's a great question. People want to know if you can sort of take like these simpler knots and create more complicated ones. And we actually had another picture that sort of showed how you did this, but we excluded it from the talk because it's a little bit more complicated. So there's something in knot theory called a link, which is basically if you think of two knots and sort of combining them together. It's a little difficult, but if you thought of two knots sort of like linking them together, that forms a link. Well, now you can start with like the unknot and form basically this link I'm talking about. That's something that's more complicated. You can do the same thing with the trefoil and sort of combine them to create more complicated things. So it's a very interesting question.
Just to add one more, I think it's useful to like try to carry this analogy between the periodic table of elements and periodic table of knots. So, I mean, it was a fantastic achievement that chemists managed to build the periodic table, but that's not the end of chemistry. Okay, after they did that, they managed to, well, by understanding how kind of things appear on this periodic table, you can take different elements and build molecules and so on. And it's really kind of similar thing in mathematics. So it's great to organize things, and that's one way we can, as humans, kind of understand complicated structures, but then we do go on to use it to do more things. So there is some kind of like molecular version of knot theory where we don't just classify and we're finished. We want to do something with it eventually. Yeah.
Okay, at this point, let's give our speakers another big round of applause. Thank you very much.